In this section, we explain how to calculate the reaction forces. When two different action moments act on a simply supported beam. A simply supported beam is a statically determinate structure with three reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in three directions. For an object at rest, equilibrium in all directions must be satisfied. The simply supported beam, we will discuss, has a hinge support at point A, a roller support at point B, and a length of L, as shown in the figure. We will determine the reaction forces caused by two action moments MA and MB. On the simply supported beam, as shown in the figure. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the three directions. Step 1. Create a free body diagram of the reaction forces. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. The hinge support at point A restrains both the vertical and horizontal movements of the beam, so the reaction forces at point A are the vertical reaction force, VA, which restrains vertical movement, and the horizontal reaction force, HA, which restrains horizontal movement. The roller support at point B restrains the vertical movement of the beam, so the reaction force at point B is the vertical reaction force, VB, which restrains vertical movement. The directions of the reaction forces are assumed as follows. VA is upward, HA is rightward, and VB is upward, as shown in the figure. Step 2. Determine all the reaction forces by applying force equilibrium in the three directions. The unit of a moment is not Newton, but Newton meter. Therefore, the moment m cannot be summed with the translational forces with the unit of Newton. A moment is a quantity that does not need to be considered in the equilibrium of translational forces. In other words, a moment does not affect translational motion, but only affects its rotational motion. We will now Analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The vertical forces are VA at point A and VB at point B. We will derive the equilibrium equation for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The force VA acts upward, so it contributes plus VA. The force VB also acts upward, so it contributes plus VB. To achieve equilibrium of these vertical forces, the algebraic sum must be 0. This concludes the discussion on vertical forces. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The only horizontal force is HA at point A. Since HA is the only horizontal force, the equilibrium equation can be expressed as follows. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for VA. The line of action for HA. And the line of action for VB. To determine the magnitude and direction of a moment caused by a translational force, it is necessary to have information about the arm length relative to the center of rotation, which is calculated from the force's line of action. In contrast, the action moment ma in the figure already has a defined magnitude of ma and a clockwise direction, while the action moment mb has a defined magnitude of mb and a counterclockwise direction. Therefore, the concepts of line of action and arm length are not necessary for the moment. Next, select the center of rotation. Choosing a point through which as many lines of action of the unknown reaction forces pass as possible will simplify the calculations for determining these reaction forces. In this case, we will select point B, through which the lines of action of the unknown forces HA and VB pass as the center of rotation. Then, calculate the shortest distance from each line of action to the center of rotation at point B. This shortest distance will serve as the moment arm length for each force relative to the center of rotation. The arm length for the force VA is L. Since the line of action of the force HA passes through point B, the arm length is 0. Since the line of action of the force VB also passes through point B, the arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point B. Let's clarify this. The force VA acts clockwise around the center of rotation, so it contributes plus VA multiplied by L. Since the arm length of HA, with respect to the center of rotation, is 0, its contribution is 0. The action moment MA acts clockwise, so it contributes plus MA. The action moment MB acts counterclockwise, so it contributes minus MB. The arm length of VB, with respect to the center of rotation, is also 0, so its contribution is 0. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on rotational equilibrium. The reaction forces VA, HA, and VB are determined through the equilibrium of forces in 3 directions, as follows. The signs of these forces are based on the free body diagram shown on the left. The positive sign indicates that the reaction force acts in the same direction as the vector assumed in the free body diagram. The negative sign indicates that the reaction force acts in the opposite direction to the vector assumed in the free body diagram. As evident from the calculated results of the reaction forces VA and VB, the signs of these forces change depending on the relative magnitudes of the action moments MA and MB. Consequently, the directions of the reaction forces VA and VB will be as follows. Based on the relative magnitudes of the action moments MA and MB,